Hey, AP Chemsters, this is Mrs. Vandelay bringing you Blankwalle, Chapter 12, Section 3. This is the energetics of solution formation. Energetics, I'm thinking of maybe energy, maybe like heat. Oh, do you remember the hand warmer lab? Hopefully you do. That was a good lab, wasn't it? Did every solution get hot when you dissolved it? No. Did some of the solutions get cold when you dissolved it? Why, yes. So this section right here is going to explain why that is, okay? So I wrote, remember the steps, all right? I alluded to this in the last section, okay? The steps of formation, solution formation. So the first thing you need to think about is breaking up the solute into individual components. So here's the individual components, whether they are polar or ionic or nonpolar, there's still an attraction for that because they're solids. There has to be attractions if they're solids, okay? So what we need to do is we need to break apart those attractions. So that is endothermic. It requires energy. So I will kind of represent this. Here's my graph, okay, of my energy versus time. My y-axis is energy. My x-axis is time. So if I start here at the solute, you must make this part endothermic because you have to add energy to the system to make those solute parts spread out. You're breaking those intermolecular forces. So what about my solvent? I have to overcome my solvent attractions too to make room for the solute. We call this expand the solvent. Look at this beaker. All right, what do you have to do? You have to expand it and take a look at this. You have to break those intermolecular attractions to make little holes for the solute particles to slip into. So that too is also endothermic. Now I gave this a different slope because I really don't know which one has more energy. They just don't have to be the same energy. Especially if this is ionic, it's going to take more energy than the water for that aspect. All right, but if this was like methanol, it'll take less energy. So I'm just giving two arbitrary endothermics, okay? Well, then what? All right, you have to allow the solute and the solvent to interact to form a solution. This is often exothermic. Energy is released as these solute molecules interact through the intermolecular forces with the solvent, all right? So when you put these together, all right, now that this has been separated, now the solvent has been separated, now the solute can slip into some of these holes there. It's like two magnets come together, wham, all right? The magnet is releasing energy in a sense when they come together. So it's exothermic, okay? So I'm going to use these green lines. Now, look what I'm doing here, all right? And oops, maybe I'll do this here too. So I don't know how exothermic it is. That's the question, isn't it? Okay. So what's the result? If adding up all these different heats of the solute, endothermic, heat of the solvent, endothermic, heat of the mixture, exothermic, is a net result greater than 0. All right, that's what this purple line is showing, okay? I have a net gain of positive, all right? This process is endothermic. Do you remember ammonium nitrate when you dissolved in water? It got cold, didn't it? All right, but what if the solute plus solvent plus the mixture, add them all up, is less than 0, all right? Like right here, okay? Then the dissolving process is exothermic. That's where your calcium chloride got hot, your magnesium sulfate got hot, okay? So let's look at problem number 5. Believe it or not, this came out of an old AP exam, all right? So let's look at this. Read the problem here, okay? It says the dissolution of ionic solute in a polar solvent can be imagined as occurring in 3 steps as shown in the figure above. In step number 1, the separation between the ions of the solute is greatly increased, just as will occur when the solute dissolves in the polar solvent. In step 2, the polar solvent is expanded to make room with the spaces the ions will occupy. In the last step, the ions inserted into the spaces are in the polar solvent, which describes the enthalpy change for each step, all right? All right, so go ahead and read this and decide what you want. All right, well, what did you pick? Well, how about this one? Steps 1 and 2 are endothermic. You have to make spaces, and the final step is exothermic. Hopefully you got that right. Came from an old AP exam. Okay, let's go to the next page. If you go to the next page, it's 12.4. So why don't I stop here? Don't wait to be great, and I'll see you back at 12.4. Bye-bye.